In this video, we will see 4 examples of solving exact differential equations. Example 1. Recall that a differential equation is called exact if its coefficients are coming from a same function. So in this example, we denote the coefficients as m and n, and we're supposed to check the y derivative of m and x derivative of n. And here, when you do the y derivative of a function, you're going to treat the x as constants. So that's why you have the 2x here copied because it's a constant multiple. And the 3x squared is going to give you 0 because the derivative of constant is going to be a 0, right? So the only derivative you are supposed to carry out is for the y squared, which is going to be 2y, and the m sub y is going to be 4xy. Similarly, for the n function, you're going to treat the y as constants, okay? Because here the derivative is with respect to x. And the x squared is going to give you 2x. So here you have the 2y constant multiples, right? And the derivative for the constant is going to be 0. And you also get 4xy. So these two partial derivatives are identical. That means the differential equation is exact. That means there is a potential function psi such that the x derivative of psi is m, and the y derivative of psi is going to be n. So these two conditions actually will give us a way to find the psi, because if we do the inverse of the differentiation, namely if we do the integration, we can get the psi, right? For example, from the first condition, you just do the integration with respect to x. So you can see here we focus on the x. And once you're going to treat the y as constant, and then it's pretty straightforward for you to get the antiderivative for the x terms. And here, for the constant, it might be a function of y. Why? Because here, once again, we consider y as constant, okay? So that's why this constant term could be a function of y, as you will see. Now, from the second condition, this time we have to do the integration with respect to y. So you're going to treat the x as constant. And then, because this is a polynomial of y, it's pretty straightforward to find antiderivatives, right? And finally, you're going to get another constant term. And this time, because x is considered as a constant, right? So this constant term could be a function of x. Okay. Actually, if you have a second look of these two expressions, you'll understand why these constant terms could be a function. For example, we have a couple of terms here, which is not observed in the second equation, right? It's just because these x terms are actually included in the C2x. Well, the reason here is when we consider this second expression, our focus is on the y. So no matter what kind of x expression you have, they are just considered as constant. Okay, so that's what's going on. And similarly, you will see a couple of y terms are not observed in the first expression. Okay, it's just because they are actually included in the C1y. Okay, now we can just collect all the terms we found over here and find our potential function. And then we know the solution to the differential equation actually can be implicitly defined from the potential is equal to a constant. And then we get the solution to the equation. Example 2. This equation is given in the differential form. And this time, we just set up our coefficients as we did example 1 and find the corresponding derivatives. Once again, when you do the y derivative, you're going to treat x as constant. That's why you have 0 here, right? And when you do the x derivative, you're going to treat the y as constants. So identical expressions for m sub y and n sub x are obtained, right? So we know this equation is exact, and there's a potential function satisfies these two conditions. So we can get the psi from the integration of m with respect to x, and it's quite straightforward integration, right? And also we can get the psi from the integration of n with respect to y. So this one is also quite straightforward. By the way, you might notice that for the 1 over y, its antiderivative is supposed to be natural log of absolute value of y, right? But we don't put the absolute value here. It's just because from the given equation, to make sure this equation is well defined, we understand y has to be greater than 0. Okay, now so that's why we don't have to carry it here. Okay, finally, we collect all the terms we got in the two expressions. We can get the potential function and the solution to the equation as the potential is equal to a constant. Example 3. Once again, we have a differential form of the equation, and we can set up the m and n as the two coefficients so that we can do the corresponding derivatives. So here, again, when we do the y derivative, you're going to treat the x terms as constants. So that's why you see the 2 0 terms, okay? And for the y squared, you're going to get 2y. And for the n function, you treat the 2y as constants, and the derivative for x is 1, so you also get 2y. So therefore, this equation is exact, and we have the two conditions to be satisfied for the potential function. And then you can just do integrations. So for example, for the first condition, you integrate m with respect to x. And for these two terms, the cosine, you can get it straightforward, right? And for the second term, we have to use integration by parts usually, right? But for this case, if you are familiar with this type of functions, you might already notice that the antiderivative for these two terms is going to be x times of cosine x. Okay, if you do the derivative for this product, you're going to get these two terms. Okay, yeah. For the y squared, because this is a constant, okay, so you're going to just get the x times a constant. And once again, you have a c1, which might be a function of y here. Well, the second condition is more straightforward because you have a polynomial here, right? Okay. Finally, we collect all the terms from these two expressions, and we get the potential function is going to be x times cosine x plus xy squared plus c. And the solution to the equation is going to be the psi is equal to a constant c, which is going to be this. Example 4. Well, this problem, the coefficients for the differentials are not ready, okay, because we got something figured out, right? So to determine the coefficients, first of all, we have to distribute this to the two coefficients inside the parentheses, okay? So namely, we're going to get, this will be the, after the distribution, this will be the form with the corresponding coefficients, okay? Once again, we have to just figure out the corresponding derivative of these two terms, right? Okay. Well, for the m part, because we are going to do the y derivative, then you notice that we have actually a factor of 3 y functions, right? We have y, we have e to the 2y, we have cosine of 2xy. So it's a product of 3 functions. So we need to use a product rule. Recall that if you have a product of 3 functions, basically you have to just do the derivative for just one factor at a time, okay? And then you multiply the other factors, and then finally you add them up, okay? So basically, that's what we're supposed to do for the m function here. So you can say we do the derivative. Of course, it's supposed to be y derivative, right? For the first term, the second factor, and then the last factor, right? For the second and the last two terms, we also need to use a chain rule. Okay, so like here, when you do the derivative of the e to the 2y, you have to do the derivative of the exponent, which will give you the 2. And for this function, you have to do the derivative of the input of the cosine, which will give you a 2x here. Okay. Well, for the n function, for the first term, you're going to say you have two factors depends on x. And the e to the 2y here is actually a constant if your focus is on x here. Okay, so that's why we have only two terms. Although this is a product of three functions, but when you do the x derivative, you're going to consider the e to the 2y as a constant. Okay, so that's why we have only two terms. And for the second term here, although we have two terms, once again, because the e to the 2y is a constant, okay, so you only need to worry about the derivative of the sine 2xy. Okay. And now for the second and the last term, the derivatives of sine and the cosine 2xy, we have to use the chain rule. Okay. Once again, you do the derivative of the cosine and the sine, and then you have to do the derivative of the 2xy, which will give you a 2y in this case. Okay. You're going to get the 2y here. Okay. Now, if you compare these two partial derivatives, you will say they are identical, right? So therefore, this equation is exact, and we have a potential function which will satisfy these two conditions so that we can integrate m and n with respect to x and y. So in particular, for the first case, you can see here, we're going to integrate this function with respect to x. And we just need to do a very straightforward substitution, and then you can get the antiderivative of this. Okay. For the second condition, this time you have to integrate a product of two y functions. You see the essential difference here is for the first case, although you have a product here, right? But the y terms are considered as constants. So your focus is only on one term. Okay. The others, they are constants. Okay. But for this second case, you're going to say these two terms, both of them, you got some functions of y times a function of y, right? Function of y times function of y, right? Now, so for this case, we have to do integration by parts. So here's the integration by parts formula, right? So for the product, we're going to consider one factor as u and another factor as v prime. Okay, now let's focus on the first term. And when we have something like this, you can just try. Essentially, you have just two factors depends on y, right? So you can try to make one as your u and the other one as v prime, right? So you have only two options, right? Yeah. And it's not very difficult for us to say that if we set up u as e to the 2y and v sub y as x times cosine 2xy, it will work. Okay. So then we're going to say, by using the formula, we're going to say some expression like this. Moreover, if you check out the new integration, you see after the cancellations, this is nothing but e to the 2y times sine of 2xy. Okay, so that's exactly the integration we found over here, right? But you have a negative sign. That means if we do substitution, then you're going to say this term, we cancel this term, right? So that means what? That means the integration of this is going to be just half of the e to the 2y and the sine 2xy. Okay, so now we finished integrating both of the m and the y, and we found pretty much the same expression, right? So that will be our potential function psi And once again, the solution of this equation is going to be implicitly defined as psi is equal to c, so that we're going to get half of e to the 2y times sine of 2xy is going to be c. Okay. And because this c is a constant, right? It's an arbitrary constant. So if we multiply both sides by 2, we still get a generic constant here. Okay. But you don't have to carry the 1/2 here, right? So our solution can be obtained in this way. Okay. To summarize, we know that if equation is exact, so pretty much you can just do the integrations, right? The two integrations to determine the potential function and get the solution directly, right? Of course, to verify the equation is exact, you have to do derivatives. Sometimes you have to use, for example, chain rule, product rule, and so on, right? And also to do integration, you also have to use integration techniques, for example, substitutions, integration of parts, and so on. Okay, well, that's all for this video, and thank you for watching.